Hello, in this video, we're going to talk about predicting the precipitation of slightly soluble salts. To predict precipitation, we can do that through the comparison between the ion products versus the solubility product of a reaction of the slightly soluble salts. Let's say we have the slightly soluble salts equation right here. To write the expression of Q and KSP, it would be the same. This is how you're going to write the expression for ion products. And if you look on the other sides for the KSP, this is the way how you're going to write it. So to write the expression, it will be the same. But what is the difference? The difference is when you want to plug in the value of concentrations, the concentrations of the cation and anion in the aqueous phase for Q may not be at equilibrium, whereas the concentrations that we want to plug into the KSP expression for the cation and anion in the aqueous phases, those concentrations will be at equilibrium. There are three possibilities when we are comparing Q and KSP. The first one is when we have Q is smaller than KSP. If we're going to imagine the situation on the scale down here, we can say that KSP value would be closer to the infinity value. And Q, since it is smaller than KSP, the value should be closer to the zero value on this scale. So do remember that KSP is the equilibrium constant. Therefore, the value will not going to change. The one that will be changing here is the value of Q. So in order for Q to be the same as KSP in this case, you can say that the reaction wants to move towards the aqueous side. Let's say we have this equation of the slightly soluble salts in front of your screen. So on your left side, you would have the solid of the salts, and on the right side, you would have the ionic species in the aqueous phases. Just now in the first example, we've seen that Q is smaller than KSP. So when you have the situation of Q smaller than KSP, and we've seen that in order for Q to be the same as KSP, it will need to move towards the right side. So when the reaction tends to move towards the right side, you are forming more of the ionic species instead of the solid species in the equilibrium. Therefore, in this case, the solution is known to be unsaturated. And do we have precipitation? Remember, precipitation refers to the production of solid, because when Q smaller than KSP, the reaction tends to go to the right sides towards the production of the aqueous species. So you have no solid being made. So we can say that we do not have any precipitation occur. The next example is when we have Q equals to KSP. In this case, when we have value of Ksp, let's say somewhere around here, the Q ion product would be the same value. Now, when you look at the situation on the scale, you can say that the reaction will not going to move to either right or left sides. So when you imagine that in this situation, when we have Q equals to Ksp, you do not have movement towards the right nor to the left. So what do we say about this solution? So the solution would be just saturated with ions. So this is what we call the just saturated with ion solution. So when Q equals to Ksp, the solution is just saturated with ions. Do we have precipitation? Also, in this case, we do not have any precipitation. The third situation that we need to look at is when we have Q bigger than Ksp. So on the scale, we can imagine that the Ksp would be closer to the 0 value and Q would be closer to the infinity value. Remember, Ksp is the equilibrium constant. You have the word constant, so it will stay there. The one that will need to move is your Q. And in order for the reaction to make Q equals to Ksp, it tends to move to the left side. When Q bigger than Ksp is what we have visualized in this scale right here, the reaction will tend to move towards the left side, towards the solid side. So when you are making more and more of this solid, you can imagine that precipitation will occur. You will see that a lot of floating solids will be observed in your beaker. Okay? Therefore, the solution is called super saturated solution. And do we have precipitation? The answer is yes. Okay, we have precipitation when the solution is super saturated. And when do we get supersaturated solution? When you have Q bigger than Ksp. So let's have a look at one example here. This is a very typical question in exams. They're going to ask you to predict whether the precipitates will occur if you are adding two solutions together. When you read the question, there are two very important things that are being given to you. The first one is the situation. First, you have the sodium chloride solution added with the lead nitrate solution to make your slightly soluble salts. We have the sodium chloride aqueous solution, this in blue, added. Okay, you have the word added over here added with 400 centimeter cubic of lead nitrate aqueous solution in red. When you add these two salt solutions together, they will be forming a slightly soluble salt solution, PbCl2, with the volume of 500 centimeter cubic. Now, the volume over here would be very important for this calculation later, and you will know why. Okay, from where do I get 500? When you add 4 with 100. So you get 500 centimeter cubic. So that is the first thing that the question gives to you. And this is how you visualize the question, by drawing them out. Second, what the question tells you is the lead chloride, PbCl2 aqueous solution, is a slightly soluble salt solution because it has a Ksp value. That is how you know whether the salt is slightly soluble salts. When the salt given in question has the Ksp value, it will be the slightly soluble salts. Right here, given to you is the Ksp value. Okay, so that is a very good clue for the information number 2 right here. And you can imagine that the slightly soluble salts equation would be looking like this. Okay, now we need to know what the question wants. The question wants you to find out the value of Q so that you would be able to compare the value of Q with the given Ksp. The given Ksp is right there, which is 1.7 times 10 to the power of negative 5. And we need to find the value of ion product Q so that we would be able to know, is it going to be smaller than Ksp? Is it going to be equals to Ksp, or is it going to be bigger? The equation right here is for the slightly soluble salts. Remember, you need to make sure it is balanced. Right here, you have the balanced equation for the slightly soluble salts. So the Q expressions should be looking like this. This is the Q expression. Make sure it is correctly written. And now, after you have found out the Q expression, you should be able to get 1 mark for this Q expression and 1 mark for the balance equilibrium equation for the slightly soluble salts. Now, what you need to do next is to find the concentration of Cl- and the concentration of Pb2+. And from where do you get that from? You're going to get that from the very soluble salts here. You're going to get the concentration of Cl- from the NaCl aqueous, the information from here. You're going to get the concentration of Pb2+ from there, and you're going to use this final volume to get that concentration. To get the concentration, you have to find the number of mole of NaCl involved and also the number of mole of lead nitrate involved. In the beginning, you have the mole of NaCl equals to 0.2 molar, and the volume is 100 centimeter cubic. So we're going to find the number of mole of NaCl involved. so that later you can use that number of mole to find out the number of mole of Cl minus, and you're going to divide that with the final volume that we have right here. So the molarity of NaCl is 0.2 molar times with the volume, which is 100 centimeter cubic, but you have to change that into decimeter cubic, and you would get the number of mole 0.02 mole. By getting the correct number of mole of NaCl involved, you would get 1 mark. So how much PbNO32 is involved? The molarity and volume of the lead nitrates is given. So you have the molarity 0.2 molar and the volume 400 centimeter cubic for the lead nitrates right here, the one in red. So molarity is 0.2 molar times 400 over 1000 decimeter cubic, and the number of mole is 0.08 mole of PbNO32 is involved. So you would get another 1 mark for that. The next step that we need to do is to find out what is the number of mole of Cl minus and number of mole of Pb2 plus. And we can get it from the information that we have done right here. First, let's have a look at concentration of Cl minus. We can get the concentration of Cl minus from NaCl aqueous. You need to know that NaCl aqueous is a very soluble salt. That's why it does not have a Ksp value that is significant. So when it says a very soluble salt, if you have number of mole of NaCl here, you can do proportionality to find out the number of mole of your Cl minus right there. So you can do proportionality like this. Okay, so from the balance equation, 1 mole of NaCl aqueous would be forming 1 mole of Cl minus aqueous. In the question, we've got 0.02 mole of NaCl aqueous, and how much is that for Cl minus aqueous? Of course, it would be 0.02. You're just going to do cross multiplication and you get 0.02 mole of Cl minus aqueous. By finding the number of mole of Cl minus aqueous, you get 1 mark. And by doing this whole thing over here, the balance equation with the proportionality, you get another 1 mark. To change the mole of Cl minus aqueous into molarity, simply use this formula. We have done this before. You can have this number of mole divided by the volume. Now, what is the volume that we need to use? Remember, you have mixed this together with the PbNO32. So the final volume will be this 500 centimeter cubic because you have mixed them together and to form your slightly soluble salt PbCl2. This is the final volume. So by writing the final volume, 500 centimeter cubic. Okay, so we should be able to determine the concentration of Cl minus. We have 0.02 mole divided by 500 over 1000 decimeter cubic, and thus the concentration of Cl minus is 0.04 molar. That is the molarity of Cl minus. You get 1 mark here, and you get 1 mark for the equation that we have done for the formula. Okay, we have found the concentration of Cl minus, so we can plug that into there, and to get the value of Q ion product, we need to find the concentration of Pb2 plus. And concentration of Pb2 plus, we can work that out the same way we have worked out for Cl minus. So right here, the concentration of Pb2 plus, we get it from PbNO32 aqueous. Also, this is a very soluble salt, so it will go for completion, and 1 mole of this salt will be producing 1 mole of Pb2 plus, as you can see from the balance equation. So when you do the proportionality, you would get something like this. So 1 mole of the very soluble salts, PbNO32, would be producing 1 mole of the Pb2 plus aqueous. And from the question, we get 0.08 mole. Remember, we get 0.08 mole of the PbNO32. So from the question, when you compare with the proportionality, so you would get the number of mole of Pb2 plus aqueous, 0.08 mole. So you get 1 mark right there and 1 mark right there. And the concentration of Pb2 plus is 0.08 mole. Remember, the final volume is 500 centimeter cubic. So 500 over 1000 decimeter cubic. And this one should give you 0.16 molar. You get 1 mark here and 1 mark right there. We have found the concentration of Pb2 plus and also Cl minus. What we need to do now, we're going to be plugging in the value of the concentration, final concentrations that we have got just now for Cl minus and Pb2 plus into the Q expressions that we have right here. Remember, the concentration that we have worked out over here are the concentrations for the mixture that we have got right there, which with the volume of 500 centimeter cubic. So we're just going to take the value of Cl minus, 0.04 molar. We're going to put that into there. 0.16 molar for Pb2 plus. You're going to put that into here. So we would have 0.16 times with 0.04 to the power of 2, and we would get the value of Q equals to 2.56 times 10 to the power of -4. Therefore, this is the Q value that we need to compare with the KSP. You would be able to get 1 mark for the value of Q that you have found. Now, we're going to take this value here and you're going to compare with your KSP. As you can see, the value of Q 2.56 exponent -4 versus the given KSP, which is 1.7 times 10 to the power of -5 is bigger. Q is bigger than KSP. So we can conclude that Q is bigger than KSP. So by doing that conclusion, you have 1 mark. And through that conclusion, you can imagine that, remember, we have the scale just now from 0 until infinity. In the case of Q is bigger than KSP, your Q would be closer to the infinity value, and your KSP would be closer to the 0 value right here. And do remember, KSP is constant, and the one that we'll try to move is the reaction towards the value of KSP, and you would have the reactions to move towards the solid side. Therefore, the solution is super saturated and precipitate will surely form. You will get 1 mark for this and 1 mark for that.